The most important continuous probability density function that we will be talking about in this course is the normal distribution. It's unimodal, mound-shaped, and symmetric. We also call it bell-shaped over here. We've briefly looked at that normal distribution a little before when we looked at the 68, 95, 99.7 rule, the empirical rule, because it tells us how our data is distributed. And here are a couple attributes of the normal distribution. The density curve for a normal variable is bell-shaped. It's symmetric about a single mode, which is right at the mean, and it has the known population standard deviation sigma. The entire area under the curve is equal to 1. So that's always with our continuous probability density functions. We have to have the area under the curve be equal to 1. And then the other thing, we can't dip below 0. So we can't have, a negative curve since there's no negative probabilities. So when we looked at statistics, we looked at the sample mean and the sample standard deviation before. When we're looking at the normal distribution, we're actually looking at the population parameter. And those parameters are mu and sigma. So mu for the mean, sigma for the standard deviation. And we're still looking at the random variable x, which has an observed value for our normal distribution. Here's our notation for the normal distribution. X follows, so that's a squiggly line, a normal distribution, and our normal distribution is fully defined by our two parameters, mu and sigma. So fully defined by the mean and the standard deviation of our distribution. Then we have the standard normal distribution, which actually is what we get when we convert our values to z-scores. Because remember, z-score tells us how many standard deviations above or below the mean a particular value is. So if we do that for all our values where we, look at each value and then determine the distance from the mean and then divide by the standard deviation in order to figure out how many standard deviations above or below the mean each value is, and we basically take our continuous random variable, which has, some value mu and some standard deviation sigma, and we're going to convert it to a standard normal distribution, which has a mean of 0 and a standard deviation of 1. This just makes it easy for us to compare values, because remember we looked at z-scores, we compared two different values, and we can determine whether something is unusual, and this will come into play when we go into inferential statistic, where we take our sample data, we standardize it to a z-score, and then we can compare it to other values on the standard normal curve in order to determine whether something happened by chance or not. And that's going to be our basic decision we make in inferential statistic. One other thing we can do with a standard normal distribution and the normal distribution, we can use the empirical rule to actually find probabilities. And we'll go much more in depth, besides our 68, 95, 99.7 rule, which just told us that, 68% of our data is within one standard deviation. It said 95% of our data is within two standard deviations, and 99.7% is within 3 standard deviations. So we'll actually be able to tell, to use tables and calculators and online calculators in order to determine what percent of our data is, greater than 2.2 standard deviations above the mean, and questions like that.